Hello. Hi. Back when I was studying circuits, I was so anxious whenever I had to solve a mesh analysis problem. And this will definitely be on the exam, for real, no joke. When I learned these simple tricks and ideas, it made mesh analysis a breeze. Look at this. Look at the circuit that we have. This is like a generic planar circuit. We're dealing with planar circuits. You can think of it as like all the circuits we're dealing with. It's just a basic circuit that you're going to see in circuits. Each like square here is like a window pane. In each window pane, we can associate a mesh current with that window pane. So this one right here would be A. This one right here, you could say that this here is B. So like current A, current B, current C right here, current D is going to be current E, F. You get it. You get it. You get it. This is like a reference direction for all the mesh currents. And they're all taken in a clockwise sense. And like they're all taken like this because it's easy to keep track of. And so we don't want to deviate for that. One thing that's curious about this, the actual currents going in the circuit may not necessarily follow the mesh analysis, the mesh current, but that's okay. If they're not following the current, that means it's going the other direction. One of the things that we see that these elements right here and this are in one mesh. So what do we do about the element that's in two meshes? What do we do about the element that's in two meshes? What we do is something like this. In a planar circuit, an element is constrained at most in two meshes, which is one see right there, at most two meshes. So there are two mesh currents that circulate through that element, and say that if some element in the nth element is in a mesh A and B, then the current through that element, this element right here, can be expressed like this. The In, the nth element, is equal to IA minus IB. So A is the mesh current, like the mesh whose reference, the reference of the mesh, basically this guy going in this direction, it agrees with the direction, the reference direction of In. So basically, if we're like formulating the mesh equations, we're going to be using Kirchhoff's voltage law, KVL. And in this analysis of A, we're going to see that this guy is in an agreement with our formation of our equation. So let me do an example. I'll clear all this up. Say we have a circuit like this, and we want to, figure out what's happening. So one of the things is that we have our mesh A, and it's going in this direction, and we have our B mesh, it's going this direction, and our C is up here, and it's going in that direction. And now we know that IA is 10, IB is 5, and IC is negative 3. So this is given to us. And now we have to find out all the currents. So for current 1, it's just going down. So we know current 1 is this. Since current 1 is going in the opposite direction of mesh current IA, so we just know that current 1 is equal to the minus IA. And that would just be minus 10 amperes. Yes. I2 is right here. Going back to what I said before. In this guy, if we're looking at like say mesh A, and if In agrees with mesh A, then this is the equation that makes sense. So I'll show it to you. So we have mesh A, and it agrees with our mesh. And we have mesh C, because this element right here is shared with mesh C. So therefore, we can write it like this. So I2 is equal to IA minus IC. because we're looking at A, and it's going the opposite of C. This would just be 10 minus -3 is equal to 13 amperes. Nice. I3 is the same thing for I3. So I3 is equal to IA minus IB. We have 10 minus 5. That's just 5 amperes. I4 is in the direction that agrees with B, but the opposite of C. IB minus IC. And that's just 5 minus -3. And that's just 8 amps. I5 is just IB, because they're in the same direction, and there's no other mesh. I6 in the same direction. I6 in the same direction as IC. So I6 is just IC. And this is just 5 amps. This is just -3 amps. This is just -3 amps. And that's it. So if you wanted to check this with KCL, what you got to do is this. At A, we have I1 going out, I2 going out, I6 going out. Minus I1, minus I2, minus I6. And that would just be plus 10, minus 13, plus 3. And it checks out. KCL checks out for A. For B, we have I2 going in, I3 going out, I4 going out. And that would just be 13 minus 5 minus 8. And that is 0. B checks out. For C, I6 going in, I5 going out, I4 going in. And that's just -3 minus 5 plus 8. And that is also 0. All of this checks out. KCL checks out. So this is all real. This makes sense. So time for another circuit. So for this guy, we just do this. We have mesh A, and we have mesh B. The idea here is that we want to use the mesh currents to express the element voltages in terms of the mesh currents. And this is what that means. For mesh A, what we just have, so the current goes through R1. So we just have R1 times IA. So basically we're doing KVL. Plus, we have R3. Remember, IN is equal to IA minus IB. So it's this. A minus IB minus VS1 is equal to 0. And that's it. So like this guy here, this guy is the voltage of this guy. And this guy is the voltage of that guy. And this guy is the voltage of here. This is KVL. So we got it. Mesh B, let's do the same thing. So this guy, so we see R2 times IB plus VS2. It's plus VS2 because the current is going into the plus. Where here, the current went into the minus. So this is going into the plus. So plus VS2 plus R3. Now think about this time. Here's a trick. Here's a trick. We have IN, but this time IN agrees with B. So like, think about this. So for the first IN, we're going down. First IN, we're going down. Second IN, we're going up. We're going up. So what this means is that IB minus IA. Because the second IN, we're imagining the current is going through the resistor upwards. And it agrees with B, but it disagrees with A. So we write this. IB minus IA. And that is equal to 0. So one thing I want to say is this. So we have our equations and we got them. You know, we got this by looking at the mesh equation. This is the mesh current. And we have that voltage here because this is fundamentally KVL. But we're expressing KVL in terms of the mesh current, which is IA. That's all that we're doing. It's simple. It's simple. It's algebra. It's just algebra. Same thing for mesh B. We're imagining that, you know, this is the mesh current. We're expressing it all in terms of B. So we have two equations and two unknowns. Two equations, two unknowns. And the unknowns are IA and IB. Typically, they are IA and IB. One thing we can do is we can find the equations by means of inspection. From inspection, we can look at A. So all the elements that are in the A mesh, we can just write this. So that we have resistor 1 plus resistor 3 times IA. And now the resistor 3 is shared with mesh B. So therefore we write a minus resistor 3 and IB. And don't forget, the mesh current is going into VS1, so we have to minus VS1. And that's it. Now this guy right here is the same as that one right there. So we have R1, R1, R3, R3, IA, IA. And minus R3 is from there. We distribute the R3 here. We get minus IB times R3, which is right here. And minus VS1, minus VS1. We got it. And then that's it. So for B, which, you know, from inspection, we can just do it again. We have R2 plus R3, IB minus R3, IA plus VS2. And that's it. That's all we got. That's it. Literally, we have it. One of the things that we frequently come into contact with, one of the problems that we encounter, we may usually have mesh equations with current sources. One of the things we have a problem with is mesh equations with current sources. What if, like, we have a current source? How do we, like, formulate the mesh equations with that? So for, like, a problem with this, VS1, VS2, these guys, see how these guys, they're, like, in series? Okay, so you look at this circuit, like, for the voltage sources, we just simply add them to the equation because fundamentally this is KVL. You can't just do that with a current source. Like, there's no KVL, like, doesn't work with a current source very well. So how do we get around this? So here's what we do. So we just do a source transformation. Say that we have something like this and we want to, like, how do we, like, make this something that we can use in mesh analysis? And it's simply this. And that's it. And I'll show you an example. That's supposed to be an in. So say that we have this kind of circuit right here. We want to find IO, but look, now we have a current source here, and this makes things a little bit more complicated. So, like, how do we deal with that? Like, what do we do to deal with that? Just do a source transformation. So I'm going to redraw the circuit for you. So I redrew this part of the circuit. So what do we do here? So if we, like, do what I said before, you know, just get this current. So multiply the resistor. So get this and the resistor, multiply them together, and then you have that. You have this configuration. So get this guy, multiply it together with that, and put this guy in series. Then we have our solution. So we multiply this by that, we get 8 volts. And it's in series with the resistor, which is 4K. So that's it. And that's it. That's your circuit transformation. Okay, so here's how we solve it. You have your IA and your IB. For mesh A, 3K times IA plus 2K times IA minus IB plus 1K IA minus 5 volts. All that's equal to 0. So for B, same deal. 5K IB plus 4K IB, 8V, so plus 2K times IB minus IA, and that's equal to 0. So the reason why it's IB minus IA is because for this guy, we're imagining the current going through in this direction up that resistor. It's going up like that. So that tells us that it's following the direction of mesh B, of the current mesh B, and the opposite of A. And that's why we wrote it like this. Now, if you were to like do this from inspection, it would just be this: 3K plus 2K plus 1K. Minus 2K IB. And because the current's going into the minus 5. And there you go. And it agrees. So 3K times the A, 2K times the A, 1K times the A, and for the B, the minus 2KB, there it is, 2K, your minus B, and minus 5, there you go. So for B, we do the same thing. 5K plus 4K plus 2K times IB minus 2K IA plus 8 equals 0. 5, 5, see that those agree. 4 and 4, that agree. 2 and 2 agree. Minus 2K, see 2 and minus 2K AI, it agrees. So these are two equations and two unknowns. And if we do solve for the currents, IA is equal to IB is equal to minus 0.6. So IO is equal to IA minus IB because it's going down. It's going down like this. So it will be going down as well. And down, it agrees with A, and it's in the opposite of B. 1.42 milliamperes. There you go. Say we have something like this. Say we have something like this, and we have, you have your mesh A, and you have your mesh B. Say you got something like this. So, like, what do you do? What do you do? Basically, it's like this. You have you see that the current source is in agreement with IA. So all you need to do is just write this, and you're done. That's one mesh equation that you know. That's one mesh current that you know. So say that you have something like this, that a current source is in two meshes. So what do we actually do if we have a current source that's in two meshes? Like, what do we do? How do we deal with this? We do it as a super mesh. That's how we do it. So we have our mesh A and we have our mesh B. So the way we deal with this is we get the current source in any element that is in series with it. And we highlight around it. We basically combine these two meshes into a super mesh. Super mesh. We write one mesh equation around the super mesh using currents IA and IB. And that's basically the idea. This guy right here is IS. That's the current source. So current source IS is equal to IA minus IB. And the reason why it's my IA minus IB, hopefully you can see, is that the current source agrees with A but disagrees with B. So you just write it like that. All right, so here's what we're going to do. So we want to find the voltage output, but we have a source in the middle. That's called IS2. And so to deal with that, you have your mesh A, your mesh B, your mesh C. So we have this, and now we want to do a super mesh. Our super mesh is this. That's the direction. Here's our super mesh. Now, to do the super mesh, we got to basically sum the voltages around the super mesh. We have to sum the voltages around the super mesh. Nice. So as the loop goes to R1, start with R1. We go to R1. Now, the mesh, this mesh right here, B, the current in that mesh, is what we're working with in this part of the super mesh. So we have R1, and R1, the current agrees with B. So we write IB, and it disagrees with A. So we write IB minus IA, and that's that. Now for R2, it's just R2 times IB. Now when we go here, we have we're in IC now. This part of super mesh, we're dealing with IC. So it's just R4 times IC. Nice. Now we get to R3. R3. So we see that it agrees with IC because we're going in this direction, but it disagrees with IA. And that's it. And that's it. We got that. Now, if we were to do it, so we did it from inspection. So from inspection, it's just the same process. So, you know, we have this going, we're going around here, start here. So so in IB, so we have R1 plus R2 times IB. And it shares with IA. So we just have minus R1 is shared with IA. So that's it for IC, R3 plus R4. And there we have it. And so like with that, we have that, and then we're sharing IA. We're sharing IA with R3. And that's it. These are the same guy. These are the same equations. R1 and R2 times IB. You have your R1 right there, R2 right there, minus R1A. There you go. R3 plus R4 is times C. R3 right there, R4 right there, R3 times IA is right there. So writing from inspection still works with super meshes. So one of the things that we have is that we know that IA is equal to IS1 because they're in the same direction. IS2 is equal to IB because it agrees with IB, but it disagrees with IC. So it's IB minus IC, and there you have it. And there you go. That's it. You did it. One equation, your two equation, and your three equation. So all you got to do is just find IC. Just find IC. And then you know V out is equal to IC times R4. So to find this, simply we just need to find the mesh equations. So now what we're dealing with right now is we have a dependent current source. It's not an independent current source. It's a dependent current source. And apparently I forgot to write it. So it's beta times IO. IO is in this direction. So IO is the current going through this source. So it's B times IO, and IO is going through the source. So now with that, I just have to write the mesh. Let's just write the meshes. Now time to let's just write the super mesh. So the super mesh, we're gonna highlight this. Highlight that. Okay, and then we're gonna basically eliminate that, and let's draw the super mesh. It's in that direction, and we have our super mesh. All we gotta do is, from inspection, think of this as essentially something that's not connected. That includes RC. R1 times your IA plus VCC, because it's going to the plus. And now we go all the way here. RE is shared with IC and IB. So we imagine that the current going through here is like this, because we're looking at this mesh. And because of that, we could normally write it as, RE going through IC minus IB. But from inspection, we can just automatically, write RE IC minus RE times B. That's from inspection. And we can also write minus VO, and that's all equal to 0. So this is our first equation. Now for mesh B, ignore that I made a mistake. So from mesh B, we can just write R1 plus RE times IB, and that is minus RE times IC, and plus V naught. So that is simply, that's 0, and that is our 2 equation. So we remember that IO, this guy right here, IO, this guy right here, is equal to IB minus IA, because it agrees. And we know that beta times IO is equal to IA minus IC. So if I divide both sides by beta, basically this equals IA minus IC divided by beta. And this guy right here is our third equation. Yeah, I did a little funky, but that's our third equation. And that's it. 1, 2, 3. We got it. So we have our 3 equations and 3 unknowns, which are the mesh currents. And that's it. This is how we form that relationship. And if you understand this, you pretty much have a mesh analysis down pat. So as a bonus, we're just going to formulate the equations. And we're doing this all from inspection. So from A, now for B. So for C, it's this. So this is all from inspection. So like if you get used to writing from inspection, you can write the equations super easy and super quick. And like that's really important to do. Because on the exam, you're going to be like stressed for time. So if you can just do something like this, it just makes it so smooth. We know how to work with even dependent current sources and current sources, and we know how to write it from inspection. It's just so easy now, right? Because like with all these techniques, we can actually solve more circuits problems. And so these techniques are like the foundations for like op-amp circuit analysis, and later for AC circuit analysis. Like mesh analysis and node analysis, they don't go away. They're here. You're going to use them for AC circuits. You're going to use them for Laplace circuits. You're going to use them to formulate transfer functions. And you're going to use it for circuit design. So, if you didn't catch node analysis, if you need some help with node analysis, like right there is some node analysis for you. Anyway, have a good day and good night. Sleep tight. Don't let the bed bugs bite. Good night.